Hello, my dear student in grade 10. This is Ghassan Masaadeh, a science teacher at Taqarrub International School. I hope you all are fine. Today we need to discuss the torque and static equilibrium, which is lesson 3 and 4 from chapter 8 from page 281 to page 296. We studied the force before and we found the force can change the speed or direction of motion for an object. Also, the force can cause a rotation for objects, and it's depend on where the force is applied and in which direction. The effectiveness of a force in causing rotation depends on both the magnitude of the force and the distance from the axis of rotation to the force. Now we can define a new physical quantity called torque and indicate it as tau, where the tau is equal the product of force and the distance, and it's measured in Newton times meter. For example, to open a revolving door as shown in this figure, a force F is applied at a distance r from the axis of rotating. If the minimum torque required to open the door is 3 Newton times meter, what is force must be applied if r is equal 0.9 meter and r is equal 0.3 meter. We know from this example the torque tau is equal 3 Newton meters, and we need to calculate the force F when r is equal 0.9 meter or when r is equal 0.3 meter. The torque tau is given by the equation r times F. When rearrange this equation, we can find the force F is equal to tau over r. When r is equal 0.9 meter, we can find the force F is equal 3 divided by 0.9, which is equal 3.3 Newton. And when r is equal 0.3 meter, the force F is equal 3 divided by 0.3, which is equal 10 Newton. So we can conclude the required force is less when it's applied further from the axis of rotation. If the force acts in a direction toward or away from the axis of rotation, what will happen? As shown in this figure, when a force acting in a direction that is directly toward or away from the axis of rotation will cause no rotation. In this case, we say that the force is radial, because it is in the same direction as the radius, and we can conclude the radial forces produce zero torque. But what if a force is at an angle theta relative to the radial line, as in this figure? In this case, we resolve the force vector F into a radial and tangent component of force F, and we can find the radial component produces zero torque, and the tangent component of F is given by F is equal F sine theta. And this component will produce a torque. The force acting the torque, or the torque, is given by, in the general equation, tau is equal R times F, or it's equal R times F sine theta, where the theta is the angle between the radial vector and the force vector. In this case, we have a new term is known as moment arm. It's the perpendicular distance from the axis of rotation to the line of the force as shown in this figure. To find the moment arm for a given force, first extend a line through the force vector. Next, draw a perpendicular line from the axis of rotation to the line of the force. the perpendicular distance, it is the moment r. And it's given by r perpendicular is equal r sine theta, referring the general equation for the torque. We can write the torque tau is equal rf sine theta, or it's equal r sine theta times f, and we can write it as tau is equal r perpendicular, or the moment r, times the force f. Now what about the sign of the torque? The sign associated with the torque is determined by the type of angular rotation it would produce. A torque that causes a counterclockwise rotation is defined to be positive, and a torque that causes a clockwise rotation is defined to be negative. Also, when there is a system with more than one torque, the net torque acting on the system is the sum of the individual torques, and we can write it as tau total is equal tau 1 plus tau 2, and so on. And when you use this equation, taking the sign for each torque. For example, we have an example on page 285. Two helmsmen is disagreement about which way to turn a ship. Exert a force shown below on the ship's wheel. The wheel has a radius of 0.74 meter, and the two forces have the magnitudes F1 is equal 72 Newton and F2 is equal 58 Newton. Find the torque caused by F1 and the torque caused by F2, and in which direction does the wheel turn as a result of these two forces. From this example, we have the radius of the wheel is equal 0.74 meter. The magnitude of the force F1 in this direction is equal 72 Newton, and there is F2 in this direction, and magnitude is equal 58 Newton. Theta 1 is the angle between the radius and the force is equal 50 degree, and the theta 2 is the angle between the radius and the F2 is equal 90 degree, and it's asked to calculate the torque tau 1 exerted by force F1 and the tau 2 from F2, and in which direction this wheel will rotate. To solve or to find the torque from the force F1, substitute by equation tau 1 is equal r F1 sine theta. Substitute the numbers where the r is equal 0.74 times 72 times sine 50, which is equal 41 in Newton meter. And the tau 2 exerted by the force F2 is equal minus r F2 sine theta. And here we substitute minus because the rotation caused by F2 is a clockwise rotation, so the torque must be in negative. Substitute the numbers, we find the tau 2 is equal minus 0.74 times 58 times sine 90, which is equal minus 43 in Newton meter. To calculate the total torque, we can use the total torque is equal tau 1 plus tau 2, which is the total torque is equal minus 2 Newton meter. Here, the total torque is negative, so the wheel rotates clockwise, and as we note, the F2 is less than F1, but it has the greater effect in determining the wheel's direction of rotation. Now we need to make a connection between linear and rotational quantities. When we are replacing the force with a torque, we need to replace F with tau and a linear acceleration A with the angular acceleration alpha, and mass m with the moment of inertia I. We obtain the rotational version for Newton's second law as the summation of the torque is equal I times alpha and its measure Newton meter. If only a single torque acts on a system, we can write the torque tau is equal I times alpha. For example, we have an example on page 286. A fisherman is dozing when a fish takes a line and pulls tangentially on the spool of the fishing reel with a tension T is equal 8.2 Newton. The disc-shaped spool, its rests initially and rotates without friction. The radius of the spool is r is equal 6.6 centimeter and its mass m equal 1.8 kilogram. What's the angular acceleration of the spool? From this example, we know the magnitude of the force or the tension is equal 8.2 Newton and the mass is equal 1.8 kilogram. The radius r equals 6.6 centimeter and we need to convert it to meter is equal 0.066 meter and we need to calculate the angular acceleration alpha. First of all, we need to solve this example. You must calculate the torque, where the torque is equal R times F or R times T. Substitute the number where the R is equal 0.66 in meters and T is equal 8.2 Newton. This is equal 0.54 Newton meter. And the moment of inertia, I is equal half mr squared. Substitute the number, we can find it. The moment of inertia I is equal to 3.9 times 10 to the power minus 3 kilogram meter square. Now, the general definition for the tau is equal I times alpha. Rearrange this equation to find alpha is equal tau over moment of inertia I. Substitute the number. The alpha is equal 0.54. This is the torque. Divide by 3.9 times 10 to the power minus 3. This is the moment of inertia. So we can find the angular acceleration alpha is equal 140 rad per second square. Now we need to discuss the static equilibrium. When an object is at rest and remaining at rest, it's said to be in a state of static equilibrium. The conditions for the static equilibrium are: the total force acting on the object must be zero. This ensures that there is no linear acceleration. And the total torque acting on the object must also be zero. This ensures that there is no angular acceleration. As an example, let's apply this condition to the plank that supports the child as shown in this figure. Choose the upward of the forces as positive. The total force must be equal 0. So in this system we have three forces, F1 and F2, and this is the F3. And we need to take the F1 and F2 is the positive, F3 is the weight for the child is a negative. So we can write the general equation for the force where the total force acts on the system when the system is at equilibrium must be equal 0. So we can write it as F1 plus F2 minus mg equal to 0. The total torque acting on the plank found by choosing the left end of the plank to be the axis of rotation. We need to take this point, this is the axis of rotation, and at this point the R1 is equal 0. So the F1 exert the torque is equal 0. And we need to calculate the torque from the F2, where the F2 caused a counterclockwise or positive rotation. So we can find the torque from the F2 is equal F2 times L. This is the distance between the F1 and F2. The weight of child, mg, acts at a distance 3/4 times L from the axis and cause a clockwise rotation or negative rotation. So we can find the torque from the mg is equal minus mg times 3 over 4 L. Now set the total torque equal to 0. We can find the 0, this is the torque from force F1, plus F2L, this is the torque from the force F2, minus mg times 3 over 4 L, this is the force from the torque from the F3, this is equal 0. Or when we move this term to the other side, we can write the F2L is equal mg times 3 over 4 L. Divide both sides with the L, we can get the magnitude of the force F2 is equal 3 over 4 times mg. Substitute this magnitude of the F2 in the force equation, where the force equation F1 plus F2 minus mg is equal 0. Substitute here F2 is equal 3 over 4 mg. We can get the F1 plus 3 over 4 mg minus mg is equal 0, or we can find the magnitude of the F1 is equal 1 over 4 mg. In this example, the left end of the plank was arbitrarily selected as the axis of rotation. In general, you are free to choose an axis of rotation that is most convenient for a given situation. Now we will describe a new term. It's called the center of mass. The center of mass, indicated as Cm, is the point at which an object can be balanced. In many ways, an object behaves as if all of its mass were concentrated at its center of mass. The location of the center of mass for two objects may be calculated using the following simple equation. X center of mass is equal m1 x1 plus m2 x2 divided by m1 plus m2. If the masses are equal, the center of mass is halfway between them. If one mass is greater than other, the center of mass is closer to the larger mass as shown in this figure. Here the location of the center of mass, when we have the m1 greater than m2, we find the center of mass closer to the m1. If m1 is equal m2, we can find the center of mass indicated as the halfway between them. If the m2 greater than m1, so the center of mass closer to m2. Also, when an object is supported at its center of mass, it is in static equilibrium, since the torques acting on the object are balanced. As shown in this figure, consider the rod is in static equilibrium. This is the rod in static equilibrium. As a result, the torque acting on this rod is equal 0. Taking the point where the rod is tied to the rod as the axis of rotation. This is the axis of rotation at this point. We can express the net torque as M1 G R1. This is at this point, this is the M1 exerted force M1 G minus M2 G R2 is equal 0. And here we have the minus with M2 because this is clockwise rotation. Or we can write this equation as M1 G R1 is equal M2 G R2. If we cancel G from both sides, we can write it as M1 R1 is equal M2 R2. This equation says that the torque exerted by the two masses have the same magnitude. So we can say the torques are balanced. Finally, as a summary for these lessons, we study about the torque, where the torque a physical quantity that is the product of force and distance, and it causes rotation. and the torque is given by torque is equal R times force F, and the unit for the torque is Newton times meter. If we have counterclockwise rotation, the torque must be positive, and when we have clockwise rotation, the torque in negative sign. And the torque acting on an object produces an angular acceleration, and we can write the torque is equal I times alpha, where the I is the moment of inertia and alpha is the angular acceleration. Also, we study the static equilibrium, and the object in static equilibrium do not accelerate. This meaning the linear acceleration is equal 0 and the angular acceleration equal 0, or we can write it as the total force is equal 0 and the total torque acts on the object equal 0. And we can find the center of mass, where the center of mass is the point where an object can be balanced. We can find the center of mass by using the equation x center of mass is equal m1 x1 plus m2 x2 divided by m1 plus m2. Finally, the balance point corresponds to the zero net torque. I will stop at this point. Next time I will to solve some problem about or regarding these lessons. If you have any question about anything, don't hesitate to contact me, and don't forget to solve the worksheet. At this point, thank you very much, my students.